Look at your monthly utility ledger. Review your behavioral changes over the last decade. You lower the thermostat in winter. You raise it in summer. You cork the windows. You run the heavy appliances only during off-peak hours. Your actual kilowatt-hour consumption drops. Yet, the statement balance steadily climbs. The arithmetic does not align, but the financial drain extends far beyond the monthly bill. Look at your utility room. Look at your kitchen. The refrigerator compressor groans audibly. The central air blower runs hot and vibrates. Appliances engineered to last 2 decades now suffer catastrophic mechanical failure in 7 years. You assume it is standard planned obsolescence. You blame cheap manufacturing. You are only half right. There is a structural deficit occurring upstream. It bypasses your smart meter. It flows directly through your main breaker panel. The regional power grid is quietly starving your home. They are not shutting off the power. They are diluting its physical pressure. You pay for 120 volts of electrical pressure at the receptacle. You budget your fixed income around that standard baseline. But test the wall outlet at 4 in the afternoon on a Tuesday. You will rarely find 120, you will find 114, sometimes 112. On peak demand days in mid-July, it dips perilously close to 110. This is not a transmission accident. It is a highly calibrated, automated supply reduction. The North American power grid is an overloaded architecture. Regional operators face a severe mathematical problem. Population density scales upward. Infrastructure remains static. Constructing new baseload generation plants requires billions in capital expenditure and years of environmental litigation. Grid operators answer to public utility commissions and private shareholders. They optimize for revenue retention and liability reduction. When regional demand threatens to exceed total supply, they do not upgrade the neighborhood transformers, they alter the delivery parameters. They shave the delivered voltage down to the absolute legal floor. You spent your working years operating under standard commerce laws. If you purchase 10 gallons of gasoline, the pump calibrates and delivers 10 gallons. If it delivers 9, that is systemic fraud. Electricity operates under a specialized legal framework. In the United States, Standard ANSIC 84.1 governs grid delivery. It dictates that utility monopolies must provide 120 volts, but it includes a legal variance threshold, plus or minus 5%. Historically, this variance accounted for natural transmission degradation over long geographical distances. It was a mathematical safety buffer for the physics of copper wire. Today, that safety buffer has been weaponized. Modern grid management software targets that negative 5% tolerance as standard operating procedure. They ride the absolute floor of the legal limit. By dropping the baseline voltage by just 3 to 5% across a metropolitan grid, the utility instantly saves millions of dollars in raw generation costs. They reduce grid strain. They prevent rolling blackouts. They protect their aging substation infrastructure. But physics demands equilibrium. The mechanical burden does not simply vanish. The utility company transfers the operational stress from their transformers directly into your home hardware. Your induction motors bear the physical load of their corporate accounting shortcut. The deficit is paid in the microscopic degradation of your property. You are unknowingly subsidizing the regional power grid with the premature death of your own appliances. Imagine a commercial diesel truck hauling 80,000 pounds up a 6% grade. The transmission is locked in gear. The RPMs are steady. The torque demand is fixed by the laws of gravity and momentum. Now, pinch the main fuel line. Restrict the diesel pressure by 5%. What happens? The engine does not simply stop. The truck does not stall. But to maintain the exact same torque output with restricted fuel pressure, the mechanical system must compensate. The cylinders run lean. The exhaust gas temperatures spike. The internal thermal load multiplies. The engine pulls the hill. But the pistons, the rings, and the engine block endure accelerated, silent wear. Your household electrical system operates on identical physical mechanics. Electricity is not abstract energy. It is fluid dynamics pushed through solid copper wire. Voltage is the physical pressure. Amperage is the volume of flow. Watts dictate the total required work. The compressor inside your central air conditioner is an induction motor. It requires a rigid, inflexible amount of total wattage to compress heavy refrigerant gas against high atmospheric heat. The physical workload is fixed. The relationship between these electrical forces is dictated by a strict mathematical rule known as Ohm's law. The equation is simple. Watts equal volts multiplied by amps. If the total wattage required to turn your compressor motor remains constant, the two input variables must balance each other. When the regional utility company deliberately chokes the voltage at the neighborhood transformer, the formula must correct itself. If the voltage drops, the amperage must rise. There is no alternative. Inside your air conditioning compressor, an alternating magnetic field pushes a heavy steel rotor. When the incoming grid voltage drops, that magnetic field weakens. The rotor loses its magnetic grip. It slows down. Mechanical engineers call this slip. To correct the slip and maintain the required torque to pump the freon, the motor pulls more raw current from your breaker panel. The amperage spikes. Amperage is heat. It is the physical friction of billions of electrons grinding through dense copper pathways. An induction motor engineered to run at an optimal 120 volts will draw significantly higher, damaging amperage when starved down to 110 volts. The motor still spins. The house still cools. You notice nothing on the surface, but deep inside the welded steel housing, the internal copper windings are absorbing a severe increase in thermal friction. The heat bakes the insulating varnish. It dries out the synthetic lubricants. The metal expands and contracts under unnatural thermal stress. Listen to an aging refrigerator when the grid load peaks on a July afternoon. The hum deepens into a heavy, grinding vibration. That is the sound of an induction motor fighting a starved power supply. The regional grid operators understand this physics. They employ structural engineers who understand Ohm's law perfectly. They know that reducing grid voltage forces millions of residential induction motors to draw more current and run hotter. They accept this transaction. It prevents their aging regional substations from overloading. The grid survives. Your hardware degrades. The corporate ledger balances. Yours bleeds. Move away from the physics lab. Step into the boardroom. The degradation of your household infrastructure is not a mechanical accident. It is a documented corporate strategy. It is called conservation voltage reduction. Industry insiders refer to it simply as CVR. Utility companies do not hide this protocol. They champion it. They draft extensive white papers for state public utility commissions, outlining its benefits. They frame it strictly through the lens of grid efficiency, sustainability, and environmental stewardship. The language is sterile and reassuring. The reality is pure amoral financial calculus. Energy is a uniquely volatile commodity. It cannot be easily or cheaply stored on a massive scale. It must be generated the exact millisecond it is consumed. When regional demand spikes during a heat wave or a severe winter freeze, the grid operator faces a harsh economic binary. They must either supply more power or they must instantly reduce the total demand. Supplying more power requires firing up secondary peaker plants. These plants are incredibly expensive to operate. Buying emergency power from neighboring grids slashes their profit margins to zero. Building new, permanent power plants requires billions in capital expenditure and decades of zoning battles. Reducing your demand is the only mathematically profitable option. Enter CVR. By utilizing centralized management software, the grid operator intentionally depresses the voltage at the neighborhood substation. They throttle the delivery down from the standard 120 volts to 114 volts. To a single light bulb, the change is imperceptible. But when that 6-volt drop is multiplied simultaneously across 200,000 residential homes, it triggers a massive, instantaneous drop in total megawatt demand on the grid. The grid stabilizes. The utility avoids purchasing peak-hour energy at premium market rates. Their balance sheet remains perfectly intact. The state public utility commissions approve this practice enthusiastically. They rubber-stamp CVR expansion programs across the country. Regulators view it as a highly sophisticated tool to manage aging, fragile infrastructure without raising base rates. But there is a massive, systemic blind spot in their accounting. The regulatory bodies measure success purely by the reduction in transmission load. They do not measure the collateral damage occurring behind the residential meter. When the utility implements a CVR protocol, they are not actually eliminating energy demand. They are merely altering its physical shape. They are forcing your heavy appliances to draw higher amperage and run for longer, sustained cycles, just to achieve the same baseline result. Consider the raw economics. A regional utility monopoly might save $50 million in deferred infrastructure upgrades and reduced generation costs by deploying CVR algorithms. Their shareholders applaud the efficiency. But that $50 million deficit does not evaporate. The laws of thermodynamics prohibit energy from vanishing. The cost is simply externalized. It is distributed across thousands of suburban neighborhoods. It materializes when your central air compressor locks up at year 7 instead of year 15. It manifests when your deep freezer burns out its relay and ruins hundreds of dollars of stored food. You call a local HVAC technician. You write a check for $3,000 for a replacement unit. You blame the appliance manufacturer. You assume they simply don't build them like they used to. The Public Utility Commission does not reimburse you. The grid operator does not log your catastrophic appliance failure on their quarterly balance sheet. To the utility company, conservation voltage reduction is a flawless efficiency matrix. To your hardware, it is a slow, methodical poison. They protect the macrogrid by cannibalizing the microgrid. They defer their own billion-dollar capital expenditures by quietly taxing the structural integrity of your property. The system is engineered to protect the monopoly. You absorb the friction. Zoom in closer. We must bypass the corporate ledger and examine the exact, microscopic failure points inside your home. We need to look at the cold thermodynamics of compressor death. This is where the theoretical voltage deficit becomes a hard, physical liability. An induction motor is an intricate assembly of tightly wound copper wire, precision steel bearings, and synthetic lubrication. The copper wire is not bare metal. Every individual strand is coated in a microscopic layer of insulating varnish, often a synthetic polymer or shellac. This ultra-thin coating prevents the massive electrical current from arcing between the tight coils and short-circuiting the entire system. This varnish is the single point of failure. It is the Achilles heel of modern appliances. When the grid voltage drops and conservation voltage reduction algorithms take over, your compressor motor compensates by drawing higher amperage. Higher amperage creates intense, concentrated heat deep within the copper coils. The motor is operating far outside its engineered thermal envelope. The failure does not happen overnight. It is a slow, methodical degradation. Heat is the absolute enemy of insulating varnish. Every time the utility grid forces your compressor to run 10 degrees hotter than its design spec, the microscopic varnish layer begins to bake. Over months and years of these silent brownouts, the polymer loses its elasticity. It becomes brittle. It begins to develop microscopic hairline fractures. Inside an HVAC compressor, this degradation is accelerated by the environment. The motor operates submerged in a bath of refrigerant gas and specialized refrigeration oil. As the motor runs hot, it scorches the surrounding oil. The oil breaks down chemically, increasing the friction on the internal bearings. The motor now has to work even harder to overcome the degraded lubrication, driving the amperage and the heat even higher. It is a vicious, inescapable feedback loop. Eventually, the brittle varnish cracks. Two adjacent loops of copper wire, carrying heavy, unmitigated current, touch. The short circuit is instantaneous and violent. The surge of uncontrolled electricity vaporizes the surrounding copper, creating a catastrophic electrical arc. In a refrigerator, you hear a loud click, followed by silence. In a central air unit, the main breaker trips hard. The compressor is dead. It cannot be repaired. It is a sealed unit. The entire system must be replaced. HVAC technicians refer to this exact failure mode as a burned-out compressor. They will tell you it happens all the time. They will blame the age of the unit. They will blame a lack of routine maintenance. They will rarely trace the root cause back to the incoming grid supply. They do not carry equipment sophisticated enough to log historical voltage drops over a 5-year period. The appliance manufacturers are acutely aware of this vulnerability, but they are operating under a different set of constraints. They face aggressive government mandates to produce high-efficiency units. To achieve these extreme efficiency ratings, manufacturers design their induction motors with incredibly tight tolerances. They use thinner gauge copper wire, They reduce the size of the internal heat sinks. They optimize the motor to run perfectly at exactly 120 volts in a controlled laboratory environment. These high-efficiency motors have zero tolerance for poor power quality. When you subject a highly sensitive, modern compressor to the ragged, fluctuating voltage of a CVR-managed power grid, the result is structural failure. The grid operator saves money by starving the line. The appliance manufacturer saves money by thinning the copper. Your hardware is trapped in the middle, absorbing the systemic friction of both industries. This precise, synchronized voltage starvation requires a specific architectural framework to function. A utility company cannot deploy conservation voltage reduction blindly. If they drop the voltage too far without knowing exactly how the neighborhood grid is responding, the system collapses into a localized blackout. They need real-time, granular feedback from every single endpoint. They need a surveillance network. Enter the smart meter. For the past decade, utility monopolies have aggressively campaigned to remove analog, mechanical power meters and replace them with advanced, digital smart meters. The marketing rhetoric heavily emphasizes consumer empowerment. They promise you a sleek digital dashboard. They promise you the ability to track your energy usage by the hour and optimize your habits. This is a manufactured narrative. The smart meter was never engineered for your benefit. It is a critical node in a centralized surveillance and control loop. A traditional analog meter is a dumb, one-way device. It simply records the total volume of power you consume. A utility worker must physically walk to your property to read the dial. An analog meter cannot measure incoming voltage. It cannot detect a brownout. It cannot communicate with the grid operator. A smart meter is a sophisticated two-way telemetry device. It continuously monitors the exact voltage arriving at your house and transmits that data back to the utility headquarters in real time, often using cellular networks or radio frequency mesh architectures. When a grid operator initiates a CVR protocol, they use the smart meter network as their eyes. They slowly dial down the voltage at the substation. Instantly, thousands of smart meters report the precise voltage drop at their specific locations. The algorithms analyze this incoming data stream. They watch the voltage dip closer and closer to the legal minimum of 114 volts. The smart meter network allows the utility to push the neighborhood right to the absolute razor's edge of failure. If one specific street drops to 112 volts and risks a total blackout, the smart meters instantly flag the anomaly, and the algorithm automatically bumps the voltage back up just enough to keep the grid online. Without the smart meter network, aggressive CVR is impossible. The utility would have to maintain a wide, safe voltage buffer to prevent accidental outages. With the smart meter network, they can strip away that buffer entirely. They can optimize their voltage starvation protocols down to the decimal point. But the architecture goes deeper. The utility is not just monitoring the voltage, they are monetizing the surveillance. The smart meter records your exact energy load profile in 15-minute increments. It knows when your air conditioner cycles on. It knows when you start your washing machine. It can identify the unique electrical signature of a refrigerator compressor versus a pool pump. This is highly granular behavioral data. Utility companies and their partnered data brokers aggregate this information. They build deep predictive models of neighborhood consumption habits. This data allows them to map out localized demand response strategies. They can identify precisely which neighborhoods have the highest concentration of heavy appliances, and thus, which neighborhoods are the most lucrative targets for targeted voltage reductions during peak hours. You were forced to accept the smart meter upgrade under the guise of modernization. In reality, you allowed the installation of the very telemetry node required to execute the algorithms that are silently destroying your hardware. The utility company used your property to finalize their surveillance loop, and they are using that loop to balance their ledger at your expense. You understand the system. You see the mechanics of the drain. The utility grid is engaged in a continuous, automated extraction of your hardware's lifespan. You cannot vote the algorithms away. You cannot reason with a public utility commission. You must move to practical, localized defense. You must armor your infrastructure. The first step is establishing a factual baseline. You cannot fix what you cannot measure. You must audit your incoming power supply independently. Do not rely on the smart meter's digital readout. That data belongs to the utility. Purchase a basic digital plug-in multimeter. You do not need an electrician's diagnostic rig. A standard model costs $20. Plug it into an unused wall receptacle in a central room. Observe the digital display. Log the voltage readings at different times of the day. Check it at 6 in the morning when grid demand is low. You will likely see a healthy 120 volts. Then, check it at 4 in the afternoon on the hottest day of the week. Watch the numbers drop. When you see 116, 114, or even 112 volts, you have confirmed the presence of a CVR protocol. You have visually identified the invisible deficit. Once you prove the deficit exists, you must physically shield the most expensive, vulnerable induction motors in your home. Your central air conditioner and your refrigerator. The most critical moment for an induction motor is the exact second it starts. This is called the inrush current phase. To overcome dead inertia and begin spinning, the compressor requires a massive, instantaneous surge of amperage, often 5 to 10 times its normal running current. If the utility grid has choked the voltage precisely when your compressor attempts to start, the motor will struggle. It will stall, overheat, and violently bake its internal windings before it even begins cooling your home. You counter this with a hard start kit. A hard start kit is a specialized capacitor and relay assembly. It acts as a localized, rapid discharge battery bolted directly to your HVAC compressor. When the thermostat calls for cooling, the hard start kit dumps a concentrated burst of stored electricity directly into the motor. It provides the massive torque required to punch through the inertia, bypassing the starved grid entirely. It dramatically shortens the high amperage startup window, drastically reducing the thermal stress on the copper windings. Any licensed HVAC technician can install one in 30 minutes. The hardware costs less than $50. It is the single most effective piece of armor you can buy for a central air unit. For your smaller appliances, refrigerators, and deep freezers, the strategy shifts. You cannot install hard start kits on these sealed units. Instead, you deploy an undervoltage protection relay, often marketed as an appliance surge protector with voltage monitoring. Standard surge protectors only guard against high voltage spikes, like lightning strikes. They do nothing against a low voltage brownout. A specialized undervoltage relay actively monitors the incoming power. If the grid voltage drops below a safe threshold, typically 110 volts, the relay instantly severs the power connection to the appliance. It intentionally shuts the refrigerator down. It forces the compressor to wait out the dangerous brownout. Once the grid stabilizes and the voltage returns to a safe operating level, the relay waits a mandatory 3-minute delay to allow refrigerant pressures to equalize and then restores power. It sacrifices a few minutes of cooling to guarantee the survival of a $2,000 appliance. The corporate grid operates on an amoral, mathematical algorithm. It views your home strictly as a load to be managed and a deficit to be exploited. You must adopt the exact same mindset. Treat your property like an isolated substation. Monitor your incoming supply. Deploy hard starts and voltage relays as your mechanical firewall. Stop subsidizing their balance sheet with the death of your hardware.